In this video, you will learn how to retrofit homes built before 1945 and homes built on hillsides. These homes all have cripple walls, and cripple walls that are not retrofitted are the #1 cause of structural damage to homes. In the next 40 minutes, you will learn everything there is to know about cripple wall retrofits. So we're going to go into the basics of a cripple wall retrofit. The way you can tell if you have a cripple wall is by the number of steps leading into the front door or back door if you happen to be on a hillside. So if you have more than 3 steps, you probably have a cripple wall. Here's another photo of a cripple wall. So for example, this is the wall right here. That's actually called the cripple wall. Right here, that's the foundation. Up here is the floor that you walk around on. And so between the foundation and the floor, this wall is called a cripple wall. So it's called cripple because it's so short, I assume. I'm not really sure why it's called that, but our big issue is it can collapse. Okay, here's an example of a house that the stairs come up here and the house cripple wall collapsed right here, a couple feet. Here's where you used to, get into the front door, the porch. Here's the steps, they're about 2 feet above. So again, this is another cripple wall collapse. This cripple wall collapsed because it had a lot of steps leading downhill into the backyard and very tall cripple walls. I saw this house in 1989 while working as a damage inspector in Watsonville, California for the Federal Emergency Management Agency. When I drove by a week later, the house had been torn down, which is a shame given how beautiful this house had once been. This is the top of the stairs, which led to the first floor. This is where the first floor was after the cripple wall collapsed. Before it collapsed, the cripple wall held up the first floor, so it was level with the top of the stairs. So we're going to talk about the cripple wall components because that's where all the retrofitting takes place. So take a look here. This is the foundation, and then this is the floor you walk on, and there's this wall right here, and that's called the cripple wall. And again, the way you can tell if you have one, here's our steps, and you have to walk up a number of steps to get to the front door. And so again, that's the floor we walk on, that's the foundation, and then this is the wall that is subject to collapse. So here's a blow up of the exact same thing. I'd like to go over these components so that you know exactly what they are. And so the first thing we look at is the foundation. So this foundation goes all the way like that around the entire house. Then over here, there's a piece of wood that sits on top of the foundation, and that's called the mud sill, right along here. Then you have the 2x4s. These are the 2x4s that are part of the wall. So here's a 2x4, here's a 2x4, here's a 2x4, here's a 2x4. So these 2x4s are also the upright portion of the cripple wall. And then here at the top, we have what's called the top plate. And actually there's 2 top plates. There's the lower one, so you see that here, and then you'll see that down here at the bottom. And then you have an upper one right here. That's the upper top plate. And there's the upper top plate here. Remember the upper top plate and the lower top plate because there's a big difference in how they are addressed in a retrofit. And then finally we have something called a floor joist. There's one right here, and then the floor joist is right here. Plus, these are floor joists. Here's one right here, here's one right here, here's one right here. And then there's part of the house that you walk around on, and that's right here. So this is the floor, and the floor sits on top of this joist. This is also one of the joists it sits on, and that sits on top of the top plate, then that sits on top of the 2x4s, then that sits on top of the 2x6, and that sits on the foundation. And when we're doing a retrofit, what we want to do is make sure that when this floor rocks back and forth, that rocking movement transfers down to the foundation, and we have to do something to the cripple wall to make sure that happens, and that's what a retrofit is. So the reason we brought all this up is because each one of these points, where it says 1, 2, 3, 4, foundation, mud sill, etc., these are all points of failure. So when we do a cripple wall to shear wall conversion, we need to make sure these points of failure don't fail in an earthquake. So for example, here we have the floor joist, and we're worried about it moving, so we put in a shear transfer tie. Then here's another type of shear transfer tie right here. Then we're worried about the cripple wall collapsing, so we put in a piece of plywood. Then we're worried about this mud sill from moving, so we put in a bolt. And then here the foundation, well we're not worried about that because that's in the ground. So when all these components are all put together, we have a shear wall. Again, a retrofit is simply a matter of converting an unreinforced cripple wall into a shear wall. Shear walls are what resist earthquakes. Cripple walls, unreinforced, are what fail. A lot of these old houses, they do fix them, they do put them back on their foundations. Many of them are very beautiful, and they don't want to tear them down because of oftentimes for their historical significance. So here's another one, again, a cripple wall collapse. This is just to show you very quickly what this kind of damage looks like. In this case, there was actually living area underneath. So right up in here, there was actually some living area, and the cripple walls were very tall, and they still collapse. Doesn't matter if they're short or tall, they all have the same problem. So first thing I'd like to point out is the cripple wall. The part up here, the things that are marked in purple, those are the components of the cripple wall. It's the wall itself. So down here we have the mud sill, here we have the studs going up and down, and then this is called the top plate up here. The problem is when an earthquake hits, there's our house, then it shakes back and forth, and then the house falls off the cripple wall because the cripple wall itself collapsed. So we need to prevent that from happening. That's the whole point of a seismic retrofit. The way that's done is actually pretty simple. You'd never think it was this simple, but all you do is you put on a piece of plywood. Here's our cripple wall, our unbraced cripple wall, earthquake force by the red arrow. That's trying to cause the cripple wall to collapse, and then we put on this piece of plywood. And it's really amazing how much force a piece of plywood can resist. For example, 10 linear feet of plywood, if it's nailed properly, can actually resist 8,700 pounds of force, which is pretty significant. And we'll go into how earthquake force attacks a house and also how plywood can and should be nailed to resist a maximum amount of force. So here's a guy nailing up plywood. It's pretty simple. You just take a nail gun and you nail it up in a certain way with certain nails, and we'll go into that again in a minute. So the way this works is earthquake force is coming here. It's pushing against the wall. Counter force is provided by the plywood, so that prevents the cripple wall from collapsing. Here we have the exact same thing. In this case, we have the foundation anchors. So the foundation anchors are holding the bottom of this assembly, this where the plywood is, holding it to the foundation. And again, here's our plywood. So earthquake force comes this way, pushing against the plywood, trying to cause the cripple wall to collapse. Then we have the counterforce offered by the plywood itself. It's also pushing down here at the bottom of the cripple wall, where the mud sill is, and that's being resisted by the foundation anchor. These two things work together. If we didn't attach the bottom of the plywood to the foundation, with these foundation anchors, the plywood could slide right off the top. Okay, now I'd like to talk to you about the foundation bolts. Every retrofit involves foundation bolts in some way. So in this case, we have a house, the hatch part right here, that represents plywood that's on the brace the cripple wall. Now, when the earthquake force hits, it will cause the cripple walls that have been braced with plywood to slide on top of the foundation unless they're bolted. So it's real simple. The house will fall like this if there aren't any bolts, so we need to make sure that doesn't happen, and we'll look at how we do that momentarily. So this section right here, that's the actual mud sill, that's the bottom of the cripple wall. So here we've got the entire cripple wall. This bottom portion is called the mud sill, and that's the part where we put in our bolts. So here's the bottom of the cripple wall. Here it is again with the earthquake force trying to push it off the foundation, and then here's our bolts to prevent that from happening. It's pretty simple. You just put in some bolts, keep it from sliding off. So now at this point we have a braced cripple wall where the cripple wall itself can't collapse, and then we've also taken that cripple wall that's got the plywood on it and bolted it to the foundation. So now the cripple wall can't collapse and the entire assembly cannot slide off of the foundation. So this is what it looks like. This is a cripple wall, and it's got our bolts. This is the studs. Plywood would have been nailed here, 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 and here, and along here, but we're just looking at the bolts right now. So earthquake force comes this way, trying to push the mud sill. Counter force is offered by the bolts. This is a very simple component. They're also pretty simple to install. So here's a type of bolts. Usually these work, that's called a wedge anchor. Sometimes we have to glue them into the concrete if it's not very good. And in some cases, if it's medium hard, these work pretty well as well. So those are the three types that you can find. Again, foundation anchors are also another type, and we saw those earlier. Wood has a quality where it can't resist a certain type of force called cross-grain bending. So right here, here's our mud sill. It's nice and flat where it's supposed to be. Now for some reason, some sort of force, earthquake or otherwise, tries to bend it like this, it'll collapse. I mean, not collapse, it'll just come apart and split like you see right here. So hardware has been invented to keep that from happening. I want to show you what happened here. This is the shear wall right here. There's the studs. And then right here, this is the mud sill. And this plywood was pulled up. And when it pulled up, it put this 2x4, which in this case is the same as a mud sill, pulled up on the mud sill, and cross-grain bending caused it to split. So we really need to make sure that that doesn't happen. All shear walls, when they're resisting earthquakes, they tend to rock back and forth, which means they pull up on the mud sill. So it's real simple. You just put on something, this is called a plate washer. So that's this piece of steel right here. It's, because you can see how it would spread out over the mud sill. It's a lot wider when the mud sill tries to split along here because of the cross-grain bending that is prevented. So this is another component of a seismic retrofit. And this is part of the building code, and it's a very important component. So next thing I'd like to talk to you about are mud sill plates. Mud sill plates are a type of hardware that were invented after the Northridge earthquake because of split mud sills, and they were also trying to strengthen the boats overall. This type of hardware right here, it has these teeth in it, and the teeth, if they're installed correctly, they prevent the mud sill from splitting. And they found it also had a remarkable increase in strength of the bolt. For example, these bolts, they increased by 59%. And then if you put one of these on the top and on the bottom, it would increase by 143%. So these are really, really good quality, important components of a retrofit, and we install them on every bolt that we put in. I'd like to point out that we are, as far as I can tell, we're the only company in the Bay Area, probably in the state of California, that uses these. The manufacturer, Harlan Metal Products, went out of business a few years after the Northridge earthquake. But we happen to have found a small hardware company that had the dies from Harlan Metal Products, and they will make them for us, but we have to order 5,000 to 10,000 at a time. But we do have a supply, which thankfully we are able to use that to protect you and other homes. So this is what those mud sill plates were designed to prevent. This is a split mud sill, and so you can see where this is the split, this is where the bolt was, and these teeth on the mud sill plates prevent that from splitting. So what we do is we put the mud sill plates on to prevent the splitting, then we put the big steel plate washers on top of that to prevent cross-grain bending. So two of those together, can't get a better bolt than that. And I'd like to show you briefly some of the things that you want to look at, and you want to talk to your contractor or engineer to find out how they are going to nail the plywood. So for example, I would like to point out this right here represents the thickness of the plywood. Right here it's 5/16 of an inch. This is if you have a nail that penetrates 1 inch and a quarter. This is a type of nail. It's called a 6-penny nail, a 6D. And then this right here is the spacing of the nail on the edges only. These nails are spaced 6 inches apart. And this 200 means that it can resist, if it's nailed like this, it can resist 200 pounds per linear foot. So if you have a foot of this plywood on a cripple wall, and then you push it with 200 pounds of force, it will fail. Anything less than that, it will remain just fine. So now let's go to another configuration. Right here we're using 15/32 plywood. That's, people call that 1/2 inch normally. And then we have the nails that penetrate 1 5/8 inches. And then we use a 10-penny nail. A 10-penny nail is much bigger than a 6-penny nail. So this is one of the really big factors here. So then we come over here, and if we put the nails every 2 inches apart, then we get a capacity of 870 pounds per linear foot. So if we go along the edges 2 inches apart, again we get 870 pounds of resistance as compared to 200 pounds if we go every 6 inches apart with a smaller nail. So this is the same right here. If you use a 15/32 and then you use an 8-penny nail, which is right here, then you'll get a 550 pounds of resistance. So these are all the different configurations. When you go over 870 pounds per linear foot, you go into an entire different set of tests and tables for high capacity shear walls, which we use sometimes, but they're pretty complicated, take a lot of extra framing, etc. But we normally use what's right here because it's simpler and building departments are used to seeing it. So let's go into a shear transfer tie attachment. The shear transfer ties attach the floor framing to the top of the cripple wall. So our cripple wall has been braced with plywood. The bottom of the cripple wall has been bolted to the foundation, but now we need to attach the house itself, the floor of the house, to the top of the cripple wall to prevent it from falling off. So right here we have a sample of the braced cripple wall that's been bolted. And over here you can see there's a rocking back and forth, and because the house is not attached to the cripple wall, it can slide off like this. So we need to do something about that, and we use something called a shear transfer tie. So this is the movement that's prevented by shear transfer ties. Right here, earthquake force is pushing against the floor joist, and then we put in these shear transfer ties to prevent that from happening. So this all occurs in this area right in here. That's your floor framing. That's again your floor joist, and this is called the upper top plate. So here's the earthquake forces pushing on the floor. You see this is the floor you walk on, so it's pushing against the floor. Counterforce is right here, provided by the shear transfer tie. So this is one type of shear transfer tie, lots of different types, but that's the basic principle. Earthquake force comes here, and the shear transfer tie keeps it attached to the top of the cripple wall. This is the entire cripple wall. It keeps it attached to the cripple wall. And then let's assume this has plywood on it. Let's assume it's bolted. The cripple wall won't collapse and the house will stay on the foundation. Here's another type. Again, here's our plywood right here. Here's our floor joist. That's the part that's supporting the floor. And then these pieces of steel attach the floor joist to the plywood, and the plywood is attached to the bolts, and the bolts are attached to the foundation, and that way ultimately the floor itself is attached to the foundation. So here's another style. Sometimes we have to use this, and this is one where we put blocks in between. So here's our floor joist. It's supporting the floor that you walk around on. We've got one here and one here, and in these cases we have to put a block. It's called the lock block in between the floor joists, and then this lock block is attached to the top of the cripple wall. Again, this prevents the floor from rocking back and forth and moving on top of our braced shear walls. When you have the plywood and the bolts and the shear transfer ties, you now have a shear wall, and this is one component of the shear wall at this point is a lock block. Now sometimes in unusual circumstances, we can't access any floor framing for whatever reason, and we actually have to staple a piece of plywood to the floor itself. So these are the staples, you can sort of see them. Staples are right here. Then we have a new mud sill, which is bolted to the side of the foundation. And so this piece of plywood was nailed to the new mud sill. This piece of plywood was nailed directly to the floor. So now when the floor itself tries to move this way, the plywood keeps that from happening. So it's always force, counterforce, force, counterforce. So here's an example of a cripple wall before it's been reinforced. So this red arrow represents the earthquake force, trying to push the floor joist off the cripple wall. And again, the floor joists support the floor that you walk around on. So when this earthquake force tries to push, it in turn pushes against the joist, and that joist pushes against the shear transfer tie. So now that movement has been resisted. So when the shear transfer tie tries to move, it pushes against the top plate, which is right here. And then when that tries to move, it goes into the plywood. Of course, you can't see the plywood here for illustration purposes. And then the plywood is nailed to this mud sill, and then the mud sill is bolted to the foundation. So what that means is earthquake force comes here, then it goes this way into the shear transfer tie, then it goes into the top of the cripple wall. The bottom of the cripple wall is nailed to this mud sill. The mud sill is bolted to the foundation, and then all the earthquake force is dissipated into the foundation, into the ground, which is what we want to have happen. So anyway, I'd like to point out the different components. Here we have our bolts. Here we have our shear transfer ties. And here we have our plywood. Again, these are the three things that we need. And every retrofit, every Cripple wall retrofit must have these components. If you're missing any of them, it can very possibly fail. If you don't put plywood on it, all the bolts and the shear transfer ties you put in aren't going to do you any good at all. If you don't put the bolts in and you put in the plywood and the shear transfer ties, great, except it's going to slide on the foundation. And of course, if you don't put the shear transfer ties in to attach the floor to the braced Cripple wall, the floor can slide off. So it's really important to have all three here. And if you get a bid from any contractor, you want to make sure that he's doing all three things, just so that you make sure that you protect your house. We were just talking about a load path, and that's the number one thing in an earthquake retrofit. Load path means when the floor rocks back and forth, that there's a path that will take that rocking motion and transfer it down into the foundation. So right here, we're going to show a sample of this. This is a tall Cripple wall, but the principles are all the same. It can be 3 inches tall or 10 feet tall. They all abide by the same principles. So this red arrow right here represents the earthquake force trying to push the floor joist off the top of the Cripple wall. When that tries to move, it goes into this shear transfer tie. That shear transfer tie then pushes on top of the upper top plate of the shear wall, where the plywood is. When that tries to move this way, that same movement goes this way and pushes against the bottom of the plywood, which in turn pushes on the bolts, which in turn goes into the foundation, which in turn goes into the ground. That's called the load path. It's really the number one thing in any seismic retrofit. You talk to your contractor, you really want to ask them, okay, now tell me, how are you going to make sure that the movement of this floor gets transferred into my foundation? Now, this is a concept that sometimes is hard to describe. And so what happens is earthquake forces on this entire floor, earthquake forces are coming here. And when the forces come here, they're going to try to go through that top plate, but they can't make it because there's a break in it. So what happens is it tries to go here, earthquake is coming this way, but it's not attached to our shear wall, which is way in the corner. When you put in your shear wall, you're not exactly sure where it will fit. So in this case, it's put all the way at the end of the Cripple wall because there were probably gas meters, pipes, various obstructions. So in this case, we had to put it all the way at the end. And what that means is that this entire part of the house is not protected by the shear wall because it's not attached to it. So this is obviously a serious problem. So one of the ways you deal with the broken top plates is with a steel strap. So here, right in here, that's where a break in our top plate is, and we take this piece of steel to attach this part of the floor to this part of the floor, and then probably down that way a little bit is our shear wall. So again, if this part of the floor moves, it'll transfer through that strap and down into our shear wall. There's another way to do that using nails. So here's a break in our top plate. Again, our shear wall is down here someplace, and we're trying to make sure that this part of the floor is connected to our shear wall. So we do this with nails. So here we put a bunch of nails on this side, a bunch of nails on this side, and the way this works, the way the earthquake force will move at this point, it goes along this upper top plate, goes through the nails, and then it goes back into the upper top plate and goes down to where the shear wall is. So just to put it on a larger scale, earthquake force is pulling this way, goes into the top plate, all these nails transfer the force over here to where our shear wall is. Now I would like to go over connecting the plywood to the mud sill. This is a critical connection. There's lots of ways to do it. Some are not very good. Some of them are quite good, and when you're talking to your contractor, you really want to make sure that he's doing the best one he can. This is a failure point, pretty serious failure point, and we'll go over that right now. If you want to know more about it, you can go to the website, and I actually wrote a paper on this, and it has all the engineering, etc. So this is the paper I wrote about this particular connection because it's so important. There's lots of information here, some narrative text, a brief explanation of the different ways, and it'll go over different code citations, opinions of different structural engineers, problems with different types. So there's the engineering here for the engineering types who want to know the engineering, the math behind these different systems. So let's go over, we're just going to go over this very quickly. This shows why the plywood to mud sill connection can be so problematic. The 2x4 is right here, that's part of the Cripple wall. are sitting on top of the mud sill, which is 6 inches wide. So we have 4 inches wide, 6 inches wide. There's a 2-inch difference. So when you put a piece of plywood on there, it just sits on top of the mud sill and is not connected to the bolts. So when the piece of plywood slides in an earthquake, it won't transfer into the bolts like we would like it to. So one of the methods to address this problem is what's called the flush cut method. In this system, what we do is we cut part of the mud sill out. So right here, we've cut out a section. So now the mud sill is on the same plane as the 2x4 studs. So when we put a piece of plywood up, we can nail the piece of plywood directly into the mud sill. So for this piece of plywood, like every piece of plywood on a shear wall, we nail it on the bottom, we nail it on the sides, and we nail it all the way around with our edge nailing. And we have a direct connection now to the mud sill, which in turn is bolted. So earthquake forces try to push on the plywood, which in turn pushes on the bolts. This is a very good way of doing it, very direct connection. So another thing that's really good about the flush cut system is that when you're done, you're nailing into this old growth wood. In this case, old growth redwood might be 800,000 years old, really excellent quality. The nails hold better, just better in every single way. It's almost impossible to split. Now here on the side, you see this is a tree farm wood, and you can see the growth rings are very wide, it's very low quality wood, and whenever possible, it's best to use the wood that's there because the quality of the wood is so much higher, it makes much better shear walls. So here's another method. This is called the reverse block method. In this method, we take our piece of plywood and then we attach our 2x4 to it. So what we would do is we would put the 2x4 right along right here, and then from the back side, we would nail it. When we're all done with that, we have this assembly marked by number 2. So we take this entire assembly and we come over here and we plop it down on the mud sill, and then we nail or lag bolt it into the mud sill right along here. So this is another way to make that connection. We like this because this long piece of 2x4 is hard to split. So here we see a sample of that. Here's the reverse block right here. There's the plywood, and there's someone who's nailing the reverse block into the mud sill. So here's another system. It's called the stapled blocking method. And in this case, we're putting blocks in between the 2x4s, and then we're stapling those blocks to the mud sill. And when that's all done, now our 2x4s are in line with the blocks, and we can nail our plywood to the blocks and to the 2x4s. We use this system when the other systems don't work. Especially, first we try to use the flush cut method, but if for some reason we can't, then we have to resort to blocking, and that's what these blocks are. So we use staples, and the reason we use staples is because it's practically impossible to split a 2x4 with staples. So here you can see all these staples we put in. You can see again, you can just see all these staples put in, and you know, there's a lot of staples. One of these blocks probably resists the same amount as 20 or 30 nails without any splitting at all. These are really, really strong, and that's our preference if we have to use a block. We don't particularly like using blocks, but if we have to. So another system that you'll see a lot of, especially in engineered designs, and you also see this in retrofit guidelines that have been published by various agencies such as the Federal Emergency Management Agency or Appendix Chapter A3 of the California Existing Building Code, Los Angeles Code, all of them pretty much. They recommend this system that uses nails. So right here, these blocks have been put in with nails and not with staples. Here's an example of a guy putting in some blocks. So here's the blocks that he's putting in. Here's the studs right here. That's where the plywood is going to go on top of this cripple wall. These are the cripple wall studs. Then we're putting these 2x4s in, and then we're going to nail the plywood to these blocks. So the problem is you can see how they split. So that's the issue. When you put in nails, the blocks split, and then naturally that compromises the retrofit. What we've seen is because splitting of the blocks is such a common problem, we see that contractors often put in nails that are much, much smaller to prevent that from happening. Because you can imagine if you do put in a nail that splits the block, it's really a lot of work to try to take it apart. So rather than doing that, they just put in small nails, which then compromises the capacity of the shear wall and can create problems in the event of an earthquake. So here's another sample. This is a block that also split, very obviously. It's not going to work as it should. And here's another one. and then you can see the split line right here, and you can see where he put the nail over here, and that caused the split. So we avoid this system entirely. We never use this system. We always use staples, or if blocking is necessary at all. As a committee member, I was able to access some people I wouldn't normally have access to, such as the lead research engineer at the American Plywood Association, who does all the shear wall testing that are the basis of the building codes in the United States and in Canada. So it's, you know, he's a PhD research engineer in charge of a very, very large laboratory. And so as a committee member, I had access to him, and I said, look, would you please evaluate these different methods of doing things, and let us know what's the best one. And when he wrote back, this is an excerpt from his letter, what he said was that the first one I showed you, the flush cut method, was the best because it most mimicked the things that they do. The next one was reverse block. If you go back up, you'll see what that was. Then the staples, and then the nailed blocking method. So I'd like to go into something called overturning. This is something that occurs to all shear walls, no matter how tall or how short. The shorter they are, the less overturning there is. We have a web page on overturning itself, and you can go there and learn more about why that is. So here's the earthquake force is pushing against the house, and the shear wall is going to try to flip over. So you can see how by that red arrow it's trying to tip over. We call that overturning. So we need to resist the overturning forces. So this is a close-up. So you can see when they overturn, it'll tear the plywood away from the nails, which again can compromise your shear wall and your retrofit. So this is an illustration of how overturning forces can cause problems. So you see on either side of this garage door opening, the walls have tipped over, they've overturned. That's what the problem is here. And the roof is just a garage roof. It's actually quite light. And you can imagine if there was a house up here, what would happen? The house is rocking back and forth, and the walls on either side of the garage door opening, which are fairly narrow, are going to want to overturn. We need to prevent that from happening. If we don't prevent that from happening, the cripple wall will fail. So here's another example of that. You can see here how there was a garage underneath this. You can see the cars right there. And you can see how this exact same thing happened. There was an overturning problem of the walls on either side of the garage door opening. So what do we do about it? That's the big issue here. Here's our shear wall. And then on either end, we put in something called the hold down. Now the hold down is a big piece of steel, and we take this rod, this pretty long rod, and we glue it with epoxy, structural epoxy. It's extremely strong. And so what happens now is when earthquake force comes and tries to flip over our shear wall, it pulls up on this bolt that's been glued into the concrete, pulls up on the concrete itself, pulls up on the entire foundation, and now it can't flip over. So here's a sample of that. So here's our hold down hardware. Imagine there's plywood on top of this and trying to pull it up. So the plywood is pulling up right here on the end of the shear wall. Again, trying to flip it over like that. When it tries to flip over like that, it pulls up here. Now this bolt right here, which is again glued deep into the foundation, prevents that from happening. So it pulls up like that, pulls up on the piece of steel, pulls up on the bolt, and prevents that from happening. So that's how hold downs work. So sometimes if the concrete is really weak, sometimes the concrete can break, and it's got to be pretty weak for that to happen, but it can happen. So in these cases, what we do is we put a large amount of concrete under where the hold down goes. So we'll fill this hole right here with a yard of concrete, and that's 3 feet by 3 feet by 3 feet. It's a lot of concrete, and it weighs a lot. Here it is in this illustration. So here we have our yard of concrete, and then here's our hold down right here. And we take a long, long, long bolt, and we go way deep into this new mass of concrete. And then when the shear wall tries to overturn like that, it has to pull up on the hold down, which pulls up on this massive block of concrete. And the shear wall cannot overturn because that's so much weight. And here's a sample of that. This is where we put all the concrete into that hole. Then here's our hold down right here, and here's our plywood. So this shear wall right here has now been protected from overturning forces. I'd like to point out here, a whole house does not need to be retrofitted. So here you see how this house in Alaska, how it fell off its foundation. Pretty big earthquake there. And the house fell, but as you'll notice, there's very little damage here. In fact, if you look right in here, you know, the windows aren't even broken. So this window's not broken, that one's not broken, and the house is more or less intact. Now the reason for that is a house is a cube. So you have a floor, you have walls, and then you have inside, you have bathrooms, bedrooms, etc., which are all cubes within a cube. So geometrically, this is an extremely strong shape. However, if they slide off the foundation, it tears out the electrical, tears out the plumbing, the inside looks horrible, and it's a pretty significant problem for anyone, not only in terms of financial loss, but the inconvenience of not having a place to live for a while. Yeah, here's another example that shows you why the whole house does not need to be retrofitted. Some people think, well, you need to start tearing off the walls in the first story and putting a bunch of plywood there, etc. That's absolute nonsense. You don't need to do that. Again, here's an example to show you why. And when I worked for FEMA, I was actually the first inspector at this house. It was in Ferndale, California in 1992. But the thing I'd like to point out is you see how the windows, the glass isn't even broken? This fell, pretty far. So here are your steps right here. They used to go into the front door. Front door is hidden behind there, and then this is the floor of the house where people used to walk around. So this is very serious damage, and again, this was cripple wall collapse. If the cripple wall had been braced, you wouldn't have had that kind of problem. So this is what a house like this looks like on the inside. You can see all the plaster has fallen off. Again, the plumbing, the electrical, everything would be messed up. So this is a pretty serious problem once that happens. So again, the retrofit would prevent that sort of thing by keeping everything together and keeping it from falling from its foundation. So I could go a little bit into designing a retrofit. I'd like to point out that we talk about earthquake forces pushing against a house. That's not the way it actually works geologically. What happens is the ground is moving, and when the ground moves like that, the house, due to inertia, tries to remain stationary, and it looks like it's being pushed. So from an engineer point of view and from a design point of view, what we do is we look at it as if it were being pushed. So this is the earthquake force moving on the ground, but if you were to look at the house, you could also look at it as if the earthquake were pushing on the house. So when we're using terms to resist earthquakes, we'll talk about pounds of resistance, we'll talk about force striking a house, etc. That's where that comes from. It's just a way of making it easier conceptually to understand. So what you've learned up to now are the practical aspects of retrofitting a house: bolts, plywood, shear transfer ties, etc. Now, in order to know how much of these components to use, you need to do some engineering. So this is the engineering we use and has been tailor-made for homes in the San Francisco Bay Area. They are the engineering basis behind a regional guideline called Standard Plan A, and even though they take some study to understand, they should be used because they are the most up-to-date, accurate, and comprehensive engineering calculations available in order to get the most effective retrofit you possibly can. So let's assume we use these calculations and figure out this house will be attacked by 16,000 pounds of earthquake force. We're now going to need enough bolts to resist 16,000 pounds of force, enough plywood to resist 16,000 pounds of force, and enough shear transfer ties to resist that amount of force. And when we figured out the capacity of our bolts, we determined that we're going to need 14 bolts total. So to resist 16,000 pounds, we're going to have to put in 14 bolts to resist that. So on this one side, we're going to put 7 bolts over here, 7 bolts over here, and now 7 plus 7 equals 14. So that gives us the 16,000 pounds of resistance that we need. So the same thing with the plywood. We determined that we needed 28 feet of plywood based on the way the plywood was nailed. And so based on the fact that it's going to resist 16,000 pounds of force, we need to get 8,000 pounds of resistance here, 8,000 pounds of resistance here to resist that force, 8,000 pounds of resistance here, 8,000 pounds of resistance here to resist forces coming in this direction. So again, we do this with plywood. You've seen that described before. Now the shear transfer ties the exact same way. So again, we've determined that we need a total of 28 shear transfer ties to resist forces in the two directions. earthquake force is coming this way. We need 28 shear transfer ties. 14 goes on this side, 14 goes on this side for a total of 28. Same thing over here. We have 14 on this side and 14 on this side, and they all resist a total of 16,000 pounds. Here's our complete retrofit. We have the bolts, we have the proper linear footage of plywood, and we have the proper number of shear transfer ties. I hope the information in this video has helped you understand more about seismic retrofitting and how to protect your own home. We're producing more videos, and if you would like to know when they are available, please click the subscribe button. Thank you.